So welcome to the 7th lecture of the course. Today, inshallah, we'll do as last as lecture 5 when we did on hands tutorial, inshallah, for training. Some announcements. First one, I would like to introduce you to Engineer Mohammed Sulaiman. So he's the new TA of the course. Inshallah, he'll be helping out throughout the semester. Inshallah, I'll add his contacts, inshallah, to Blackboard. So, yeah, if you want to, TA, teaching assistant. Yeah. And so he's now. He will be the new instructor. If you're fine with me, I can let him be the instructor. But what's going on? Okay, someone else is messing up. So let's see. Yes, please. Thank you very much. Okay. So, no, I'm still the instructor. He's Mohammed is a PhD student, and he'll be helping out throughout the course as a teaching assistant, inshallah. Okay, so he'll be helping out throughout with the project, and if there are any things related to the course, inshallah, you can ask me or him, inshallah. That's the first announcement. The second one is that assignment number 1. How was it? Good, bad? Everyone had it. I think I had someone asking me to delay, but I don't know if it's the part of this course or the other one. Is someone called Ziad? Ziad is here. You don't have anyone called Ziad?
We have.
You have one?
Yeah.
Yes. He's not here yet? Okay. So, okay. Did you face any problems? Okay. Don't expect the exam to be this easy, okay? So this was only like... Of course, exactly. So the purpose of the assignment is to help you through the learning. So it's not to assess you. So this is called formative assessment in the sense that it's helping you to know what to learn, what to study, okay? So now if I ask you what the difference between a humanoid robot and a quadruped, you all know, right? Because you've all looked for pictures. I don't need to give you to tell me what is to memorize what the definition is. You've all experienced it by hand. So again, that's the idea. You've all experienced and had a lot of ideas on the differentiation between fully observable, partially observable, and the rest of the properties of task environments. So when I ask you now about it, I can ask you simpler questions than the one that you had to really think about it. You know how to solve. Okay. So again, so the purpose is for you to develop the skill, not really to memorize stuff.
Regarding the last question,
yeah.
For example, if it is coming in the exam, will it be specified?
To be extremely specific. To be extremely specific that it will only have one answer. Okay. And if it has 2 answers, and I'll always leave the justification box in the case that you really think about something that's even slightly different from the one that's explained, you also have the room to explain it for yourself. So again, there will always be room for tinkering with it a little bit. For the homework. You mean for the fully observable and the stuff? What I'm gonna prepare, inshallah, is I'll prepare. I don't know if we're gonna have time before the exam, before the quiz. That's the third action. Now, so there's a quiz. There's assignment number 2 and there's a quiz. So quiz number 1, the quiz number 1, you're gonna see more of the stuff that might come in the midterm exam. Okay, so quiz number 1 will be similar to the midterm exam. The assignments are different. So the assignments teach you more stuff and you have more like different skills, but the quiz will be similar to the one that's coming in the exam. And the answers to I might devote some part of the session to discuss your answers actually on the assignments. So stuff that are clear, everyone, I will not discuss them because everyone got them. Stuff that are controversial or some wrong answers, I'm gonna capture these and then you can check whether I actually got them all right. So I'm gonna have part of the session. It won't be a whole session dedicated like last time, but inshallah I'll try to make it part of the session before the quiz or before the midterm exam. Cannot promise yet.
When the quiz?
Quiz 2, I'm gonna send the announcement. I think quiz 2, assignment number 2 deadline will be next week. So by the end of next week, assignment number 2 will be posted, inshallah, today or tomorrow. It will be a programming assignment. So assignment number 2 will be related to what you're gonna see today and to the previous programming session. So it will be programming on Google Colab. That's assignment number 2. Quiz number 1 will be theoretical. Okay, studying stuff that we covered so far. Okay, include even the stuff, the theoretical stuff that's included into the program.
After the assignment.
It will be after the assignment, probably with 1 week or 2 weeks. I'm gonna announce both, inshallah, today, the exact dates and where they will be. Everything will be the assignment. Assignment number 2 will be similar. Will be also on Thursday, 9 o'clock, so that you submit it, you get rid of it. The quiz will be in Wednesday, this Wednesday, in a Wednesday class. Okay. I'm gonna the exact details. I do it on the run, so it might change. I cannot promise. No. Okay. What? Probably 4 assignments and 2 quizzes. Probably. They might increase.
So each 1 to 5%.
Exactly. Okay, that's the goal. Yeah, exactly. Okay. Okay, so are you ready? So who revised CNNs from the COE course? I read send an announcement to take a look at to run to go through the previous code. That was the first suggestion, and the other one is to revise the computer vision mode topic that you had before. Who did the previous programming session? Okay. Who did the revision of the course? Okay. So we're gonna suffer a lot today, unless you really remember that stuff, because there won't be a lot of time to go through the explanation of the concepts. But again, yeah, ask if there's anything that's not clear. Today, inshallah, we're gonna be training CNNs, convolutional neural networks. Again, we're gonna be using Keras and TensorFlow. In this course, we're gonna be doing some relatively heavy training than last time. So CPUs actually will be very slow. So make sure when you're running this tutorial to actually choose from the runtime that you're using GPUs. And Google Colab gives you some free GPUs that you can use, but again, it's not. They're very limited, of course. And so that's a very good question. I haven't done it yet, so I don't know. So you can check out online resources. Definitely, I'm pretty sure it's possible. I think from here, so I think you can connect to a local runtime or something. I don't know. Maybe you can try it yourself, but I'm pretty sure it is possible. Yeah. Okay. Another way to do it is that you can install Jupyter notebooks on locally, and then you can run it from there. That's also another possibility. And you can run the notebooks inside. You can from the command line you can run Jupyter, and then it will open for you, for example, like in a local browser. You can access you can upload the notebook, and then you can see it and run it in an interactive way similar to this. Okay, so let me ask a question. Is this what this image is doing? Is it familiar or not? Okay. It's convol. Exactly. This is the convolution operator, right? You have 3 things in a convolution operator. You have an input, which is in this case the image, a 2D image. Convolution is a general mathematical operation. It can be done to 1D signals, can be done to 2D signals, 1D input. Let's put it this way, so it doesn't require a sequence. It's 1D input, a 2D input, or a 3D input. So convolution is general, and what you see here is convolution in 2D. Okay, so you have a kernel, which is another 2D array, which is the one that's shown here in yellow. And if you look at the on the lower right, let's see. It's a good idea to increase the size. Okay, if you see on the lower right, corner of the yellow filter, there are small red numbers. There are red numbers, right? See, it's one from left to right, from the top 101, 010, 101. Do you recognize these numbers? So this is the kernel. So this is called the filter. Other name is called the kernel, and we're convolving it in this 2D image, and the output is another image or another 2D array of different size. Okay. All clear? Is that clear? Okay. Are you familiar with the name with the word padding? Padding. So here, when we're doing this convolution operation, we started with the 5x5 image, and we're getting as a result a 3x3 image, right? And the filter that was used is 3x3. The relation between the output image, the output size of the image, and the input size of the image, okay, is very clear. So you have a very clear equation that how to get the output from the input. And if you're using padding, this equation changes. Padding means that if you look at this image, sometimes filter size might not fit in with the image, especially with the corners. So you might say, okay, I want to fill in the corners, for example, with either zeros, or I want to fill the corners with the same as the previous image. Okay, so this filling of the corners is called padding, such that you can get in the end another, the same size. Okay, have you seen this before? The padding, this ring bell. Okay, what we're gonna doing it here is without the padding. Okay, so this is why the image size decreases, and you've definitely seen the operation of kernels before, because if you've used any of these operations, any of basic image processing operations, like for example, sharpening the image, increasing the contrast, increasing the brightness, doing some edge detection, all of these simple operations, they are done using convolution. But in these operations, the filter itself is already predefined. Okay, so the kernel itself has a specific value. So here, for example, you see the blurring operation. You've all seen, we've done blurring before. Blurring. So if you have an image and you do some blurring effect, that as if it's like it's in motion or something, this is called a blurring operation. It's simply a kernel with all ones. So a 2D array all full of ones, and then you divide by the sum. So it's like taking a mean, taking the average. This is what the blurring operation does. Okay.
That's the meaning of lattice matrix on the image.
In a convolution fashion. So you convolve this kernel with the image. So this is the input image, and you use this filter, you do the convolution, and you get another array again, but here we use padding so that you get the same size. And you see this is the result.
So it is like the previous 5x5, and you pass this matrix on.
Exactly. This is the convolution. Exactly. This is the output. You pass this filter, you get this output. You pass this filter, you get this output. You pass this filter, you get this output.
So when we pass, we get smaller.
Exactly. That's why I said you use padding, so that if you use padding, okay, to fill in the corners, you get the same size in the end. That's possible.
So padding?
Padding. It's called PADD.
So
ING.
The result will be the same size.
Exactly. You fill in the corners, you fill in the missing spaces that you had, such that you get the same image. This is the idea. Okay.
How can we know which one?
That's a very good. This is, you remember we've I think at some point, yeah, you remember at the when we introduced deep learning, do you remember what the difference between there was an image about the difference between the deep learning and the machine learning. Do you remember this image? Where the machine learning had first you do some feature extraction and then you do some classification. But here in deep learning, we have the feature extraction and the learning both at the same time. Do you remember this figure? Okay, go back to it. I think if you have your tablets, you can look it up in the lecture of when we introduced the deep learning. The feature extraction part is the design of these filters. Okay, so these filters, with these numbers, they do this operation. So they are designed by hand. Okay, so this is already like it's like a mathematical form of these filters. They're already set. If you want to do edge detection, use this filter. If you want to do averaging, use this filter, and so on. Okay, and you can do it the other way around. You can put the numbers inside of the filter and see what the operation does. Okay, so this is the feature extraction part. Now in deep learning, we use these filters, but we don't put numbers in here. We put them as arbitrary weights. And then what do? We train this network. What does training mean? It means we optimize for these weights. So we learn these parameters, the parameters of the filter. We learn these numbers that are inside of the kernel throughout the training process. And then we do exactly the same that we did with fully. You don't exactly. You don't tell it what you want. This is the difference. If you tell it what you want and you give it the numbers, then what does the learning do? It doesn't. It's not learning these numbers because they are preset. You're using convolution and you're doing the operation, and then you tell it do the classification. This is machine learning. In deep learning, you keep these filters variable, so you keep them with some numbers unknown. You start with some numbers,
you do the training, and then you update these numbers and so on. Okay. The task of today, inshallah, we're going to be training on a new dataset. This is called the CIE483 dataset. Okay, CIE4 stands for the Canadian Institute for Advanced Research. This is one of the biggest institutes with top scientists of AI. And they produce this dataset for you. That's also a labeled dataset of, I think it has also, well, let me see it. I think, yeah, 60,000 32 by 32 images, but they are colored images with the RGB mapping. So each, if we look at any sample of this dataset, what will be the size of that tensor? It will be 32 by 32 by 3. Exactly. So each image is 32 by 32 by 3. It's a 3-dimensional tensor. Okay. Last time, what was the size, if you remember, from the MNIST dataset? 28 by 28 by 1. Why? It was a grayscale, so it had a value from 0 to 255. Here we have the same. We have 3 channels, each is from 0 to 255. Okay. It's a good point. So CNNs are, you can think of them, they are a fundamental part of computer vision now, okay? Because what people used to do is that you have these features, so we know how to do edge detection, we know how to do mean, we know how to do all of these operations with the filters. So one way of thinking about it is that, okay, let's have pre-designed layers where you get all of these features and then give them to a machine learning algorithm that can do the classification. Okay, but when people started using deep learning, they got performance that outperformed everything else that people saw. If you remember the diagram from last time with ImageNet, so ImageNet had 1,000 classes. Okay, it was unbelievable the performance that you can get with deep learning. So people in computer vision now, it's an essential part, and it's not only for classification; it's also used for image segmentation and other applications. So CNNs, they are taught now in computer vision applications. It's not only used in computer vision, but it's widely used in computer vision. Let's put it this way. And okay, this is a robotics class. Why are we talking about CNNs in a robotics class? Exactly, because everything that, and this I think we mentioned before, all advancements in CNN computer vision and all advancements in natural language processing, they are immediately part of robotics, right? You don't need to think about it. But as a roboticist, you use them as a tool. And this is what we're practicing here. So if you want to learn about CNNs and how to, and more stuff, you typically have some image processing application, and then you use it for that, just for training. Okay. But this doesn't mean that you cannot use CNNs for robotics applications. Okay. So now let's start running. So this is again the stuff that we're gonna have. We're gonna have again. So today we're also gonna have new stuff throughout the learning. Okay, stuff that could also be applied for to feed forward neural networks. But again, we're looking at them today because you're supposed to practice the homework, like the last tutorial, and now you're very good at training neural networks. But let's assume you did that. So now we're gonna load the dataset. So this is again, so the CIE483 dataset is included in Keras. You can easily include it. Last time with the MNIST dataset, the index of each class was already the class label. So we had label 0 and 1, 2, 3, 4, 5, 6, 7, 8, 9, which is exactly the same. Same. This was the index also of of the labels that you have in the array. But here the labels they have. So if you look at if you print, for example, any of the test labels here or any of the train labels, you'll find that they have from 0 to 9. So you just want to have a map from the 0 to 9 to the actual names. So that's why you need to have these class names written by hand. And if you look at the shape, and let's also get a number of some of these random sample of these figures to look at them, just like what we did before. This is the output. Okay, so we have a 50,000 samples We have 50,000 samples for training and 10,000 for the testing, for the validation, for the testing. And each of them is 32 by 32 by 3. And the labels are just one dimension, but the labels come from 0 to 9. Okay, so these are the classes. So that if you see here that, okay, when we read this, the class, we use the class name so that you can get what type of it. And you see these are typical numbers. Any comments so far? Any questions? Any observation on the images?
So like the previous
Yeah.
presentation, right?
So
You're just showing the labels and their name.
exactly. Okay.
Not clear.
Very good observation. Yeah. First of all, they're very small, right? They're only 32 by 32. And they're out of focus, right? If you want them to be more focused, you need to make them bigger, add more pixels, and then it'll be higher quality.
Is it the original photo or zoom in?
It is the original photo. Yeah. So this is really what's used for the training. Any comments on that?
Using the
Why do we use very small images that are really out of focus? Why not very high quality, 10,000, like 1,000 by 1,000 pixels of resolution? What?
Will be better if we use our focus and train for the bigger one.
We don't train for the bigger one, actually.
Fine.
The time for training and the data, one point is actually the memory that you require. So when we're running the training process, we take all of these 50,000 images. So 50,000 by 32 by 32 by 3 bits, so bytes, okay? Or if you do it smartly, and then so you multiply it by the number of bytes, you get a huge, okay,
So each
amount
pixel-
of memory that you need.
Each pixel has 1 byte, right?
So from 0 to 255, you need this 256. How many bytes do you need for that? I think you need, this is an 8-bit representation.
So 1 byte.
Not sure, 1 byte from 0. Yeah, 1 byte. Yeah, 1 byte is enough.
But what I need if it's
Because this is only the input layer. Now the weights will be float variables. They are decimal points. So now imagine that you have the weights, right, of this size, and you have the output layer and so on. So the weights will be huge. I'm going to show you actually the weights in a second, okay? The number of parameters, okay, for very simple networks. But if we increase this from 32 to 32 to 1,000 by 1,000, you immediately see that how it scales. Okay, so from 32 to 1,000, you get a square scaling. Okay, so it's by 2. So the number of pixels grow, quadratically. That's a big problem. Another thing, which is actually in the computer vision itself, to do the classification, it's enough to have these images. You don't really need that much of a high resolution to do a classification. Okay, so that's the idea. So classification can be done actually on these low resolution images. That's enough because they already have the information for a classifier, for a computer to say that this is an airplane and this is an automobile and this ship and so on. Some of the images will be very difficult, by the way, but most of them will work. Okay, so that's the idea. So even if you have a data set with high resolution, to do the training, actually you sometimes reduce the quality of them. And if I give you in the test phase a high resolution image, you reduce the size, so you do a compression of it, you reduce the size, and then you do you make it enter to the model, and then you get the classification, and then that's enough.
That's the number of the pixels itself will be different size resolution image. For example, a specific color.
Yeah.
Gray. It will be different if the image is high resolution or not.
You're gonna have more pixels. So when you have more pixels, then the number itself will not. So here it has only 32 like 3-dimensional arrays that for each pixel tells you the value of R, G, and B. Okay. Now if and this 32 pixel is, for example, in let's say 1 inch. Now if I add more pixels, you're gonna have more. If I add more pixels in the whole image, there will be more pixels per inch, which is this is what you mean by high resolution. That's the idea. Okay?
What if we use another way to represent the picture? other than
another color map,
another way.
another color map. So for example, like there's the CMK or something like that, other color maps. The network will not identify it. So you have to do the conversion first. The network is trained for RGB images. Okay, so it will associate the values that it has inside to these images, to this input. If you give it a different input, it will not know. Okay.
I mean, what if we use that way same time?
But this is a different color map, but you still have three numbers, right? So with the CMK, for example, you still have three numbers. Other color maps, as far as I know, the RGB gives you three numbers. There, I think there are more color maps, so more channels, but I don't think there is less. I'm not sure. Okay, it's something that you can look at. Okay, but with respect to the training, it doesn't matter. Okay.
What is this number? 873?
Wait.
1704.
Where are you looking at? Here. I have no idea. Probably, yeah. I think there's like time steps for the. This is the download part. So at the first thing that we did is that actually it downloaded the dataset. So this is what it does. It downloads it from the website where this is hosted. Okay. So it's not included in the package itself. You run this command and then it downloads the package. Okay, from somewhere else. Yep. Okay, this one. Yes, because this was a random sample. So what we did here is that you see, what did we do here? Yeah, we did a random sample from 0 to, yeah, from 0 to the length. Okay, so the from the train images, yeah, 60,000, and then we got these nine. We got 9 images randomly. Okay, that's why there are twice. Yeah. Okay. What we're gonna do is that we're gonna normalize the pixels again from 0 to instead of from 0 to 255 from 0 to 1, same what we did last time, and we're gonna transform the labels to what's called the one-hot encoding, in the sense that instead of having classes 0 to 9, we're gonna have classes 0, 1, 0, 0, 0, 0, 0, 0, 1, 1, 1, and so on, like we did last time. Okay, and you look now at the shape. So the labels now are 50,000 by 10 instead of 50,000 by 1.
So each layer will be divided by 255 in this case.
Yes, exactly. What the train images was, if you look at here, so the size was 50,000 by 32, 50,000 by 32 times 3. Each one of these is already a value from 0 to 255. So when you divide by 255, they all get normalized from 0 to 1. Okay. So it's normalizing pixel by pixel. So this is the total number of pixels. So if you multiply these 4 numbers by each other, you get the total number of pixels. Yeah, total number of pixels, because actually you have number of pixels, 32 by 32 pixels in the R channel, in the B channel, and the G channel. Okay.
This is a 3-dimensional.
It's a 3-dimensional tensor. Matrix is by definition a 2-dimensional tensor. Tensors is more general, and this is actually the motivation of the name TensorFlow, the whole library, because it's made for tensors. So 1-dimensional tensors are vectors, 2-dimensional tensors are matrices, 3-dimensional tensors are tensors. Okay.
So why the one-hot encoding is 5 ones?
One for the train label and one for the test label.
But we have printed the training.
Oh, so that's all. Yeah, you're right. Absolutely. Let's do this. I think. Okay, what I did now is that I did something wrong. Can anyone know what is it? No, what I did now is that I ran this again. So the train images now were divided again by 255. Okay, so this is completely wrong. So what we need to do is that we need to reload the data. Okay. So these small tricks, be aware of them when you're doing the assignment number 2. Okay, because you might be reloading the same variables. Okay, and you forget where they are.
Before we compare to what exactly we compare?
The labels. So instead of from 0, 1, so the class 0 will be converted to 1, the rest are zeros.
So each
Class
label-
1 will be 0, 1, the rest are zeros, and so on.
Each label will be array.
Exactly. Instead of from 1-dimensional to 10-dimensional. So that's why the output from 50,000 to 10.
And what also will be tensor or array?
It's also all of them are tensors. In this case, it's a 2D vector, 2D. It's a matrix, okay? Rows and columns.
But I mean now each pixel has a value from 0 to 55, right?
Yes,
And you divide it and
it became from 0 to 1,
then you
and then I divided again when I changed this typo.
went out encoding converting it like 001, 0005.
No, but I ran this whole cell, so this was included. This was the problem. Okay, so this when you ran this, so we divided train images by 255, and then we put it in train images, and then when I ran it again, it took the train images divided by 255 again. So this was the problem. Okay.
Can you zoom in?
Yes. Better? Okay. So this is the first network we're going to be building. Okay. First, it has a convolutional layer with ARELO activation. And then we're going to have a max pooling layer. Then we're going to do another convolutional layer with max pooling. We're going to flatten the image, okay, because now it was an image, okay? It was a 2D. We're going to flatten it, so we're going to convert it from a 2D array to a 1-dimensional vector, and then we're going to connect in the end a classification part. Okay.
So based on what you choose, what's going to be the convert?
This is the typical way of doing convolutional network. Usually you have convolutional layer and maybe another convolutional layer, and then after that you add max pooling. This is a typical, you can think of it a typical unit, and then you can stack more of these.
So what the result or the output of each convolution?
Okay. The output of each convolution layer, okay, given some arbitrary filter, will take the image and put something like this. So it will take the three layers of the image and give you 3 layers of the convolved value.
And
Each convolved feature will have something that looks like this, but you have no idea what it is.
So, but it's only part of the array.
Yes, but it's still a 2D array, so it's a new image.
So we call it feature map.
We call it a feature map, exactly. It's a feature.
So how many feature maps we have?
That's a very good point. You choose. Just like when you were choosing the number of layers, the number of neurons in a layer, for example, for the feed-forward neural network, you choose how many of these filters that you want to stack. What we do here in the code is that we say that we want 32 filters. Okay, so we want to have 32 of these filters.
For each layer, right?
What?
For each layer in the RGB.
For each layer in the RGB, what we can do actually is take a look here. So this is the output after the conv layer. So the conv layer, one thing that you can actually see here, this is a nice library that you can use, and it does the following. Okay. So this is a way that you can visualize the layers that you have. So one way that you can visualize is the summary of Keras. So you can, when you do model.summary, okay, this is the output that you get. You can always check what are the input and the outputs. And you also check the number of parameters of each layer. Okay. So number of parameters here are the parameters that you're going to be training, you're going to be learning. And this is the same, but just visually. What you see here is that first we have a convolution layer, that this is the output, this is after the image, the input layer comes, and then you have this convolution layer.
So
After scanning, you get this layer. This is the number of layers. This is not one layer. This is actually 32 layers. Okay, so these are
32 for each layer that we have in the actual image.
Take a look here. We have no. We don't have for each channel, you mean?
Yes.
No. We have only 32 of these.
For the whole channel.
For the whole channel, exactly. Okay, because the filter itself So here, the filter itself that we had was three-dimensional. So here, what you see is that this is a filter, and so which is a 2D 3x3 matrix. It's a 2D tensor, 2D tensor, and you have the image, which is the green one, is a 5x5 also array matrix, 5x5 matrix and a 3x3 matrix. In our case, we have a 32x32x3, and the filter will be f by f by 3. Okay, so you're gonna convolve all of the three layers together, and you're gonna get the output would be only one layer. Okay, and you're gonna stack 32 of these convolved feature.
And each one of them will be smaller than the actual.
All of them will have the same size. So now the output is, all of them will have this size. So now you can see the output here is 29x29. So you get 29x29 matrices, and you get 32 of these.
It's smaller.
So what we started with was 32x32x3. We did the convolution layer. The output is 29x29, so slightly smaller, okay, by 32. So we got 32 of these filters. You can think of them as 32 channels. That's also one way. But we don't call them channels because they have a different purpose. Here there are 32 features, exactly. This is for one image, exactly. Only for one image, okay?
And what is the 1560?
Very good point. What is this number?
Weight.
The weights of what?
The intensity of each box in the conventional matrix.
In the, again, in the what? What are these the weights of? The filter, the kernel. So the kernel is the only thing that's unknown here. It's the only thing that I pass through the image. Okay. So the input is 32x32x3. Okay. And the size of the kernel is fixed. Where did we fix it? Here. So here I said I want to have a 4x4 kernel. Okay. And it has the same number of channels of the input. So it's a 4x4x3. The input is 32x32x3. Okay. So this is the size of the image. And then how many filters do you want to have? 32 of these. Okay. So now let's check. So 16. Now let's do a calculator. So we have a 4x4 matrix. How many parameters does this have? 16. So this is for each kernel, it has 16 parameters. How many kernels do I have? 32. 512. Okay. What is missing? 3 layers. Okay. I think we passed. Yep, we're almost there. 1568.
Plus the bias.
Plus the bias, exactly. You have also
What is
bias.
the bias?
Okay. 1536. Yeah. Plus the bias, which is 32. So you have one bias for each.
But the bias will add to the value, not to the matrix.
Because the input, so the filter, again, because when we're doing the convolution, we can also allow for a small offset. Okay, this is also possible. And then for small increment, only one dimension. So you have plus the number of filters that you have. So it's plus 32.
So look, we converted 3 dimensions to 2 dimensions, right? 3-dimensional tensor to 2-dimensional matrix.
No, but each image was 3-dimensional.
Yes.
And it was 32x32 by. We still have a 3-dimensional tensor here. See? The whole data set was 4-dimensional because we stacked them with the 50,000 images. That's why you had 4, but in the end, they're all 3. So 3-dimensional to 3-dimensional.
And 32 here, this is the number of each filter.
The number of filters, exactly. Okay.
The size of the filter depends on what 4x4.
Your choice.
And can we apply a stride?
Yes, you can apply stride. Yes, exactly. You can apply stride. You can also choose the padding. Here we did no padding. That's why the output was slightly less. Okay. And if you change here the filter size, you get even a different output shape. Okay, because it depends on the filter number. So this output is from a formula that comes immediately from the input size and from the filter and also the stride and also whether you're using padding or not.
But
Okay.
also, we don't interpret the value of the
The size of the kernel, you choose it. It's a hyperparameter, but the values of what's inside is up to the network to train. Okay. This is after one layer. Okay. What you see here is that this is a feature map. Remember what we said before on the image itself. So a high resolution image it has much more information than the one that we need for the classification. The same also for the features. If I'm only interested in only learning about edges and circles that are present abstractly in the image, I don't need this much of a size. So that's why we can do downsampling. This is what the max pooling does. Okay, I'm pretty sure you've seen the max the pooling operation before. You can do a max pooling or average pooling. Okay, this was in the computer vision topic before. Okay, so this is the first.
max pooling extracts certain feature that we want.
It does downsample, exactly. It just downsamples the thing by 2. Okay, because I think we had this a 2 by 2 okay size, so it just that reduces it by 2.
Actually, it takes the most important feature, right?
Exactly.
Based on
Again, you choose whether you want it to have a max pooling or an average pooling. It's part of the architecture. You choose. It's a hyperparameter again.
so max pooling will give you the edges of
Max pooling will see all of the features, all of the that will see the 29 by 29 this matrix, and it will try to reduce its size by taking only the highest values of it. This is what the max pooling does.
and that pooling
Takes the average exactly of each part.
So now the convolution is only kernel filter. So what's the purpose to have the activation?
Because if you only do the convolution, you still have this idea. You still have this idea of non-linearity. Remember that we still want to have this non-linearity such that you can have more expressiveness of the network. Same idea. Okay.
So it does not do anything in the filter itself.
No. It's after the filter. Okay, so it's an activation after the filter. You do the convolution, the operation, you get it, and then you do the filter. You do the activation, the non-linearity.
we have neurons.
The neurons now are not pixels. So what we had in the previous lecture is that we had each pixel was considered to be a neuron, and that's too much. What we do here is that we have the output, the layers, each one is an image. That's why it's a it's a two-dimensional array.
This radio and this activation function, where it
It will act on yeah, okay, I see your point. It will act on 2D image, assuming it's pixel by pixel. It will act pixel by pixel. Okay. So this is a typical way of doing. You always have convolution and pooling. Convolution and pooling. Sometimes you have 2 convolutions and then pooling, 2 convolutions and then pooling, and then you stack more of these. How many of these? This is the architecture that you have. And what you expect is that the output after each max pooling is a feature map. It's something that you can look at, and you hope that the network, for example, is trying to do some edge detection here, do some I don't know, maybe some color mapping, divides the red alone, and for example, divides the pink alone, takes the yellow alone, and so on. So more maps within the RGB channel. Okay, and then in the end, we add a normal, fully connected layer. Okay, 2 layers of them. This is exactly what we had actually before. Okay, if you remember from last time, we had 128 neurons, and then afterwards 10 layers, which were the classification, and this was the input immediately to the input image. Okay, so you see, so the last 2 parts were actually from last time, but now what we're saying is that we add more layers, but instead of adding more of these layers to be just fully connected layers, we put them as convolution layers because we're treating images, and images have this structure inside of it. Okay.
What is the layer before the output?
This one. This is the hidden layer. It's a hidden, fully connected layer. After the convolutions, or after all of the convolutions, we end usually with this fully connected layer that can even have more hidden layers. Okay.
Then we have this one, this, and this one.
Yes, of course. You can have dense and what?
We have hidden layer,
Yes.
100,000, and then we have 1,200. The rest.
These are the number of parameters. Not this is the layer size. This is the number of parameters inside of it.
What was the last two rows?
They represent two dense layers. So if we plot this, you're gonna see in the end like a column of layers, a column of layers. This is a 10, this is 128, and this is a flattened image, okay, which will have a size of 800.
The dense layer represents the results after applying activation function of
Yes. At the very end, and they also have activation function. Exactly, they have their own activation function. Okay. We compile the model. Okay, we're going to use the same settings as we did for last time. We choose a batch size and epochs. Here we're going to have a large number of epochs because this will take some time. I should have run this from a while ago. Okay. And this is the point where you take a break and so on.
What's 391?
Where?
I know, below the arm.
This one. That's a very good question. So what is 391 here? This is very important to know. Does anyone remember from last time? How does the stochastic gradient descent work? You remember?
take a group of
We take the 50,000 and what do we do with them?
divided
Divide them into?
epochs.
No.
No group there.
What was the name? Batches. Exactly. You divide them into batches. How many batches?
I didn't.
You choose. So we had here 50,000 images to train. So we had 50,000. And then we divide them into 128. So this was 390. So again, we put in each batch the same number of images. So the 390 of them will be whole, and the last one will have less. So the remainder one is 391. Okay. So the last batch, okay, so this is 391. So the last batch will have less images. It will not have the same as the other ones. Okay. Are we getting a good accuracy?
So each epoch, as you said last time, to go through all the image, right?
Okay, for each batch, we take a part of the, you assume that your data set has only, let's see, has only 128 elements, 128 images. And this is small in size. You can put in the memory, you can calculate the gradients for it, you can optimize the gradient, the parameters for that. And then you get a number, but that's not the whole data set. So you do it again after optimizing for 128, you do it for the next 128, for the 100. We're still in only 128 images, and we do that for all of the 128 for all of the 390 batches until you end. Then afterwards, you've went through the whole 50,000 images, right? So this is one epoch, and then now it's as if you've done optimization only once, divided into smaller problems. Then you repeat the optimization 40 times. So here we chose 40 epochs. Okay, and this is the result that we got. We reached a result of 91%. Is enough, or shall we continue? Enough. Okay. Now let's try it on the images. The test. What is the accuracy? 66.8%. Why is that?
The mixture was key.
Why is that? Does anyone have a
Different features.
no? Overfitting, exactly. That's called overfitting. I did very good on the training and very bad on the testing. Overfitting. Okay, so this is overfitting. So how can we make sure? Can anyone explain or remind us of what the overfitting was?
It's not achieve a very good accuracy at training, and then it's when you test it very long.
Okay, this is how you know it. But what is the model doing in this sense? Can anyone explain what from the perspective of the model?
It fixes the weights on some features, but they are not fixed for all the images.
Exactly, they're not generalizable. You've learned very well how to classify the images that were inside of the training data set. But if I give you something that's new, you haven't really learned to identify the features that are in birds in general or in airplanes in general, right? Because you were very, very specific to optimize for this data set. So there are, and this is a huge area of research, right? There are many techniques that you can do or try again or play around with so that you can prevent this overfitting from happening. Okay, the easiest one is actually, instead of doing the training, okay, on all of the samples that you have on the 50,000 images, one thing that you can do is that you can take a part of these images, let's say 10% of the 50,000 that we're playing around, that we're training on, and you can, during the training, you can try to do something called validation, in the sense that you do the testing while the training and you see what's going on. Okay, can I generalize or not? If not, you don't add these images to the training, but what you do is that you play around with the hyperparameters. Maybe you're learning too much, maybe you're learning too fast, maybe you're learning too slow, and so on. So you can use these to have some automatic tuning of the hyperparameters while training. Okay, and you can also have a criteria that you stop once you reach, for example, let's say 80% accuracy. Because if you exceed 80 or let's say if you exceed 90%, or if you reach 100% in the training, you're very likely that you've overfitting the model. Okay.
How to increase without over?
What?
How to increase the accuracy without over?
You don't want to increase. You don't want to the training accuracy to be very high. You're really interested in the testing accuracy, not in the training accuracy. So even if you get very low training accuracy and very high testing accuracy, that's very good. Okay, but the opposite is not.
So how can we know if we can proceed to the testing?
That's the testing data you only use when you say I'm done.
Yeah, how can I know that I'm done?
You don't know, because you usually don't have the testing data in the first place. If you deploy the model, for example, and this is now a camera model that you want to test it here on a real application, you don't know whether this is a bird or not. So you don't have the test data. Okay, so this is part of the. It's actually, if you think about it, it's part of the training. Because now I tested the data. What I'm gonna do now is that I'm gonna use this. I'm gonna change the model, right? So it's part of the. It's not training. It's not part of the optimization, but it's part of developing the model. Okay, you use this test data. So this is really not the. You can put the real test data. You can think of it this way, where you deploy this application, and for example, like ChatGPT, and then people start using it and start finding out there are stuff that are wrong with it. This was not clear in the test data that was trained on, okay, or validated on. Another way is techniques called dropout. Have you seen dropout before? Have you heard about it? Okay, so the dropout is simply in the fully connected layers. One thing that you can easily do is that you can randomly set some of the neurons off. Okay, so a nice image I think of it is a famous image of it. It's actually
This technique to avoid all.
yes, yeah. Why does dropout prevent overfitting? Because when you make the neurons inactive randomly, you force you make the learning harder. You force the network to start. You force the neurons to start relying on not to rely on the same features that they've been learning, to start learning new features, and this allows for generalization. So this is one way that was again, these are all heuristics proposed and tested, and things work. Do they have any theory and well understood math behind it? Of course not.
If we turn off one neuron,
Yeah.
other neurons will let a new feature.
Again, this is randomly. This is not throughout the whole training process. This is only per batch. So for one batch of images, you train these neurons, and these neurons, for example, they get good at detecting edges, and in the next batch, randomly they change, and so on.
Like we specialize there.
Absolutely, it's a specialization. Exactly. This was the motivation behind. It's exactly like preventing specialization of the neurons. Okay. The third technique, and this is really considered to be very well used, and it has empirical evidence that's very powerful. It's called batch normalization, and this is it's very complicated to explain it only in a few minutes. But the idea of batch normalization is that after each batch, you look at the statistics of the sample that you had within this batch, and you start to make sure that the output statistics is the same as the input statistics. This is the idea. Okay. So instead of, because if you don't do that, what happens if you have very deep networks, so layer after layer after layer, is that the statistics of the samples, they start to to change drastically. So when you do the normalization, you make sure that the statistics remains the same. So again, just doing some calculating the mean and the variance of the network of the input to each layer. Okay.
So for each layer you calculate the mean.
Not to each layer. What you do is that you add some batch normalization layers somewhere in your network. Again, this is like trial and error. So maybe after, so usually what you have is that you have a convolution, and then a batch normalization, and then the activation, and then so on. So
What's the benefit of this batch normalization?
this is what I'm saying. It prevents this phenomena. It's called the internal covariate shift. Okay, which is related to changing to make sure that the mean and the variance of each batch does not change throughout when you go deeper throughout the network. Okay, so this is one way of doing it. And the third, the last one is data augmentation. Data augmentation is very smart, because what you do is that we had only 50,000 images, right? Can we increase this data? Can we make it more? So we were only given 50,000 images. Can we make it into more? How? What? Rotating it a little bit. Exactly. So then you get 50,000 more if you rotate it only by one angle. Right? If you rotate it by more or randomly, you can increase. What else? Yeah, maybe. Do you expect the test values to have different colors? The test images? No. But you can expect that in the test images, I won't see a dog that looks only straight. I can have a dog that's rotating a little bit. So I would like to learn the features of the eye, and for example, the edges also rotated a little bit. Translation, okay, it's not important, because actually the convolutional neural networks, the whole idea is that actually they give you some invariance to translation. But what you can do is also flipping, right? A dog that looks like from eye to left is different from dog if you flip the image. So flipping horizontally, vertically, and so on, all of this you can do. So this is called data augmentation. You can do it to the data itself and then have a bigger data. That's one way of doing it. Or you can add it as layers within the network and then make them act randomly. So what it will do actually is that every epoch, it's as if you're giving the network different images to train on, not exactly the same images. So this prevents overfitting.
So
Okay.
one of certain layers will see the picture, for example, flipped.
Exactly. So during some epochs, you're going to have the same images, but flipped, rotated, shifted, and so on. What?
Rotation, flips, and scaling.
Scaling is having the size bigger. Again, 32 by 32 images, but instead of the dog being small, instead of it being bigger.
Increasing the number of data that we train on has no relation. We have overfitting or not. Like,
Exactly, absolutely. Actually, you can increase the data, okay, and then you still overfit, right? But that's why data augmentation can be used to increase the data set, or can be used within the layer to add some sort of randomness. Okay. Overfitting, yeah, it's a general term. It's simply if you learned the training data set very good, that it's very hard to classify anything that's outside of this training data set. This is the idea. Okay. Now this is a more complicated network. Again, why did we use it? Yeah, because I found it on the internet. And it will have, okay, I will actually start, let me visualize it, and I'm going to start also the learning, because it's going to take a while until if you have any questions. So let's see. So this is, let's see. Just make sure it's starting. Okay, now we can take a look at it. So this is how it looks, okay? So first, I have a sequential layer. This sequential layer, okay, is actually, I built here some random data augmentation layers, okay? So I do random flip. Okay? So a picture has a probability that when it comes, it will be horizontally flipped, or not. And I do a little bit of translation. Okay, just a little bit, not too much. Okay, because when you translate, you change the image a little bit.
So sequential mean add more data.
Sequential is that it's like a sequential layers. Okay, so you add layer after layer after layer. Okay,
Of what? Of the image.
Of these operations. Okay, so this is the data augmentation part, and then you see we add this data augmentation
Before the input. Shouldn't be for the images.
You see here, this was the input layer and this was the data augmentation layers. So I do it this way. So I build this sequence. I build these data augmentation layers outside so that you can play around with them, and then you can add them inside of here. So this is one way to add them instead of really having it inside of the network and changing the network. Okay. And then we have actually before I had it like this. Okay, but you see now it depends now where you put them inside of the network. But if you always want them to be after the input image and you want to play around with them and maybe turn off one and not the other, this is the way to do it. Okay, because in this way actually if I comment this one, I can turn off the data augmentation completely. So this is one way that you can, one easy way of programming.
It's like we have more data or more layer.
It's like adding randomness in the data set. So not always so by this way of data augmentation, I'm sure that each epoch, I'm not going to train on the same images.
Now
Okay.
we have 50,000 images or more.
Each for the network, it always sees every epoch 50,000 images, but not the same images, because some of them get flipped, some of them get translated, and so on. Okay, so it's as if you have a bigger data set and you're training on some of them or not.
So we have random translation.
Yes.
To random rotation.
Yes, the random rotation is like this, and the random translation is like this.
The whole photo.
Of the photo, yeah. And then on the other side, you start to fill it in with some way, because yeah, maybe what gets out from this side goes into this side. This one way of doing it. Okay.
So
And-
in the convolution part, it will be the same 50,000 image or also change through
The pooling.
this
Uh,
convolution part will be changing this 50,000 or
no, remember the 50,000 is the data set.
okay.
When we look at the input to the layer is only one image. So on one image, and then it goes through these layers and so on.
And then when we start training, each epoch will see different 50,000.
It will have 50,000 images, but there's a high chance because of this randomness that it will see different. It will not. We're sure that it will not see the same images. This is what we're sure of.
And the convolution or the training?
In the whole training, no, in the whole training.
Training or not?
The data augmentation will change the input image. So you see, we give the image to the input layer, it passes through the data augmentation layers. So there's a chance that it passes as the same way that it entered, or there's a chance that it changes. So now it's a different image from the last epoch, and also from the future epochs. Okay. And then we have typical, as I said, we have convolution, and then batch normalization and activation. This is important. The batch normalization, it has to be done before the activation and after the convolution. So this is the way it's done. Okay, for reasons I will not explain now. So you see, we have convolution, batch normalization, and activation, convolution, batch normalization, activation, and then we have one pooling, and then we have the same here. You see, so we have one convolution operation, convolution, convolution, convolution. So we have 4 convolution layers and 2 pooling in this way, and afterwards we flatten, and then we add some dense layers in the end, and not only doing densing, we also have some dropout here. So the dropout, you remember that it activates some of the neurons and not. So it's as if we're having a weaker network in the classification in it. So this makes it harder to train.
So in each epoch, some neuron will.
Exactly. And we're done. Took a long time to, yeah, relatively slow, of course. So we reach about, yeah, almost 80% of the training. But now let's see the testing. Okay, 77%. That's good enough. Okay, we won't try to go further. Okay. So now I'll just show you, this is something called the confusion matrix. I think you've seen it before in the previous calls, the confusion matrix. Okay. The confusion matrix is one way that you can really see, yeah, Now it's too big. This is one way that you can see the performance of your network. What is it? What is it classifying very good and what's classifying less good? Okay. So here you see trucks from the 1,000 images that were in the test dataset. It got, sorry, and then I think it was 900 images, something like that. So it got 866, very good. No, I think it was more than yeah, it was 1,000 images. So it has an 86% for accuracy in classifying trucks, 93% in classifying frogs, 94% in classifying automobiles, same for airplanes, very high. But you see what is the worst classification score it has? For dogs. And it usually mistakes dogs for what? For cats. So its classification of dogs and cats is very bad. But the classification for the rest is very good. So this is one way that you can, after the training and after the testing, you can now look at and try to see what is the network doing wrong? How can I increase? How can I maybe make it better and so on? So this is a nice way of debugging. And the last thing is that we're gonna look at some images and see what is the network really getting wrong. So for example, this is a picture that it says it's a cat, but it was a dog. Is it intelligent? Yeah. If you give this to a baby, like just a toddler, he might also confuse this to be a cat, right? It's not really clear that it's a dog. This one is very stupid. The network thinks it's a frog. Okay. Does anyone know why it thinks that it's a frog from this image? Can anyone guess? What? Yeah. What's in the background?
Green.
The green, right? So the network learned that green is associated to frogs, and there was a green here. So it has some percentage that this is a frog. And then the percentage of the frog was bigger than the percentage of the dog. So it says it's a frog. Airplane and ship. You see, airplane and ships, usually it confuses from each other. Why is that? Exactly, because also of the background. Usually ships will have a blue background, and also airplanes will have a blue background. So it's hard to tell. Okay, and so on. This is a truck, but it was a bird. Right? Yeah, it says a truck. Okay. This image is not even clear to me. That's the deer side. So the network is correct. It sees a lot of green, says it's a frog, and so on. Okay. So this was the tutorial of today. The last thing I want to show you is that this is a very nice link if you're curious. So we stopped only about 70-something%. And this is a very nice tutorial of, these are really very complicated networks with much more than what we discussed. And you see here, yeah, some of them reach the 95% of accuracy, but you see how much time it took for training?
95 accuracy when they tested.
This is after testing, of course. Yeah. When they say accuracy, they by default they mean testing. The training is you already you don't brag about the training, right? It's something that even if the training was low and you got the 95% accuracy, this is what they're looking for. And you see here the size of parameters. The size of parameters that we had with the complicated network was similar to this one. So it was almost 900,000 parameters. And we trained it in like minutes. So actually, we got a 75% score. So we got similar to the Lee-Con network. The Lee-Con network, the Lee network is really one of the oldest networks, one of the milestones of AI, right? And I think we mentioned it before. It was done one of the first where convolution was used with neural networks, and it was done for the image for character recognition and so on. Okay. So you see, this one had 62 parameters, and it got the same accuracy that we have. So we have a much bigger model that's really, that the Lee network actually already beat. Okay? But they required more training time to train, okay? Because they went up to 20 epochs. We only got this accuracy with 20 epochs. Okay.
They are different architecture of the CIE.
Absolutely, the completely different architecture. Now I put this link for you if you're interested in looking at any one of these. You can go and explore what these networks are doing. Okay.
What our last architecture called?
What?
The last our last CNN score.
For the test, it was 77. It was similar to this, 77%.
The
Something.
name of the architecture that we use.
It's you call it, if you want to coin that name, coin it. Okay. It was just something I found on the internet. I'm not sure if it might be even one of these, but I'm not sure. I'm not sure. I think it's just something, yeah, from there. Assignment number 2 will be posted today, inshallah. We're gonna have 2 questions. One which is on building a fully connected network, like in the previous tutorial, and one here on building a convolutional neural network. Take a look at the assignment. If you have any questions or something, just post it. We're gonna also have a discussion board for that. So that's it for today. And let's see, stop sharing.